Okay, so good afternoon. My name is Radek Hranický. I'm a PhD student from Brno University of Technology in the Czech Republic. On this picture, you can see our beautiful campus in Brno. And the topic of my presentation is distributed PCFG password cracking. So you may wonder what the PCFG stands for. The PCFG stands for Probabilistic Contact-Free Grammars. And those are a mathematical model that can be used for various purposes. It was originally first used in the area of linguistics for processing of natural language, but it was soon adopted to other areas as well, including ours, which is about passwords. So you can use a grammar to make a mathematical model of user passwords. You can assign different probabilities to these passwords or to their fragments, and thus you can model how users behave when they create their passwords. Such a model you can later use for measuring password strength or crackability. So you can distinguish between weaker and stronger passwords. But of course, you can use this for smarter password cracking, which is actually our use case. So how does this work? You have a data set of existing passwords. This is called the training data set. And you process it automatically. Based on this processing, you get some knowledge. And such a knowledge is represented by a mathematical model, which can be, for example, a probability matrix, a grammar, syntax tree, semantic tree. There are different options. But in our case, it is a grammar. Then you can use this model to generate new password guesses. And those password guesses, most of them haven't existed yet, but they still they follow the patterns from the original data set. So their form, their syntax respects the behavior of users that created the original passwords. So the goal here is to get as close to the reality as possible. And this is an example. Here you have a word list made of 2 passwords. This is pass, exclamation mark, and word, and laugh, add laugh. And here you can see the resulting grammar. Every rewriting rule here is assigned a probability value. So you can see, for example, that the fragments word and pass, they have the probability of 25%, while the fragment laugh has 50%. This is simply because it occurred twice in the training data set. Yeah, while the others, they occurred only once. Pass is here once and word is here once as well. From this grammar, if you apply all possible rewrite rules, you can generate up to 24 different passwords. And so this is a much higher number than in the original data set, as you can see. And what is important here, that these passwords are in a probability order, from the most probable to the least probable one. So the goal of the PCFGs is to create, of their use in the password cracking, is to create more probable passwords first. How to get the probability of a password? It's quite simple. It's a product of probabilities of all rewrite rules that were applied when this password was created. So, for example, we have a password hello free, and you want to know what is the probability of such password. This password was created from the start non-terminal using these 4 rewrite rules. You can see here the probability of these rules. So just by multiplying these rules with each other, you get the final probability of the password hello free. The original idea is from Weir, who originally proposed the use of PCFGs for password cracking and presented it in this nice paper and also another ones. Also his PhD thesis as well. And Weir, he created a proof of concept tool, which consists of 2 applications. One is called a PCFG trainer, and the other is a PCFG manager. The trainer is used for processing the input dataset and creating the grammar, and the manager simply generates the password guesses from the grammar. So how long it takes? This is a single machine approach using this CPU. If you take a dark web 2017 dataset, which is one of the freely available dataset then leaked from different website attacks, you can download it freely at this GitHub page. If you take first 10 passwords from this dataset and create a grammar from it, and then generate all possible password guesses, it takes less than a minute. If you take 100 passwords instead, you are still under a minute. But if you take first 1,000 passwords, then the generating takes more than a day. So how to deal with that? We can, for example, distribute this somehow. And another motivation for distributed computing here is that on the previous slide, it was just generating the passwords. The cracking consists of two stages. One is the generating, and the second is the verification of it. That you take this password, you calculate some hashes from it, and then you compare it with what you try to crack. Yeah. So what about the actual cracking? This table shows an example of a measurement. This is a brute force attack using a single machine with NVIDIA GTX 1080 Ti, and it shows the worst case time that is necessary to crack an alphanumeric password made from 6 to 10 characters using that is securing one of these 3 formats. So, for example, you wanna crack an 8-character alphanumeric password of securing Office 2003 document. It takes at most 23 hours. Cracking a WinZip password of the same length and structure takes about a year, or could take about a year. But this is just a single machine. If you stack 20 of these machines, you can crack the Office within an hour and the WinZip within maximally 2.5 weeks. So for serious tasks, the distributed computing is often the only way. So we decided to distribute this PCFG-based attacks, but how to do this? The idea is to use the existence of so-called preterminal structures. So what exactly is a preterminal structure? It's a sort of a partially generated password. Concretely, it's a sentential form where all possible applications of rewrite rules lead to strings with the same probability. So every password that you generate from this grammar, it originates from some preterminal structure. This illustration shows it. Here you can see the start non-terminal by different rewrite steps. You sooner or later proceed to one of these preterminal structures. So if you get this one, then on this structure you can apply whatever rules you want, whatever are possible, but all the passwords that you have that originate from this preterminal structure will have the same probability value. Yeah, the probability of these 3 passwords is the same. So this is the basic idea. So we can use this preterminal structure because we are sure that whatever is created from it, the probability won't change after that. Yeah, so we can even distribute it. So the first step in our effort was the parallel version. The original version from Weir was written in Python, and our parallel is written in Go language, which is a compiled language from Google, pretty fast. And how it looks. This is the architecture of our parallel solution. There is one Go routine. Go routine is a sort of lightweight thread, and it generates the preterminal structures and puts them into a priority queue. Then through a buffer channel, they proceed to 1 to n go routines, where the n is selected to respect the number of processor cores that are available on this on the given machine. And each of these go routines, it takes a preterminal from this channel and it generates all possible password guesses from it. And then through an output buffer, it's flushed to the output, to some word list or possibly some password cracking tool. This idea was presented in a paper called "On Practical Aspects of PCFG Password Cracking" on DBSec conference in Charleston, USA. So the results of it were pretty nice. I think this is the comparison of the original version and our parallel version. We tried. This is an experiment on 3 different grammars, and we were measuring how many password guesses are we able to generate in 10 minutes. So you can see that in all cases our solution is much faster. It's about from 8 to 40 times faster than the state-of-the-art tool. So now let's proceed to the distributed version, which is actually the core of this paper. We assume a network that consists of a server, as you can see here, and a bunch of clients, which serve as the GPU-accelerated cracking workstations. The naive solution here is to simply run this PCFG generator on the server, generate the passwords, and then send this password over the network to the clients and make the clients verify these passwords. Make the clients do the cracking from the passwords received by the clients from the server. However, this solution, because you need to transfer all these passwords to the network, it has relatively high requirements on the network bandwidth, and also because everything is generated here on the server. And if you generate using this PCFGs, if you generate passwords for multiple client nodes, it's pretty complex. Yeah, so it has high requirements on for the computing resources on server as well, not only the processor but also operating memory and so on. So our solution, on the other hand, is the server does not generate the passwords, the final passwords. It generates only the preterminal structures, and they are sent over the network, and the clients generate the final passwords from these received preterminal structures. And from the passwords it generates, they do the actual cracking. Yeah. So the generating is, even the generating, not only the cracking, is distributed here. The architecture of the server looks like this. Here we have a generator which generates the preterminal structures and stores them in a buffered channel. Then when a client node requests for work, because the clients, they are actively requesting, in our use case for new work, it receives a chunk of 1 or more preterminal structures. And the size of the chunk is calculated adaptively to the performance of the client. Yeah, so based on the settings of this tool, it tries to adapt to the current capabilities of the cracking network. The server also maintains information about the connected clients, like which client has what chunk assigned at the moment. It can also be used for live cracking, so the server maintains a list of non-cracked hashes and a list of hashes that were already cracked. As a failure recovery mechanism, it stores a list of incomplete chunks. So in case of a failure, if some node goes down or fails to complete the chunk for some reason, the chunk is saved here and is later reassigned to another node, for example. The client is looks like that. It takes the chunk received from the server, and this chunk contains some preterminal structures. The client simply takes these structures, and here it is very similar to our parallel version. Yeah, so it generates the password guesses in parallel from these preterminal structures, and these passwords are sent to a pipe. From this pipe, they can be either sent directly to the Hashcat tool, which we natively support, or if the user chooses, they are sent to the standard output where they can be redirected to any other cracking tool or to some dictionary, whatever the use case is. Yeah, so in this aspect, our tool is pretty flexible. Yeah, you can use Hashcat, you can use any other cracker, you can just save it. It depends on what the user needs. The result of the cracking session is then reported back to the server, so the server can update its internal state, it can update its structures, and so on. The protocol here is pretty simple. The client connects to the server. First, it receives the grammar, the list of hashes to be cracked, and the type of algorithm that we are cracking. Then this goes in a loop. The client asks for new work. It receives these preterminal structures in a chunk. And once it is done, it sends the result. And the server responds by sending OK. This repeats until we have any passwords to try, or until all the hashes are not cracked. Yeah. Once the cracking is over, the client sent disconnect message and the server responds with OK. Technically, this is built on the gRPC and the protocol buffers technology. So let's see the results. This graph shows the cracking speed, the achieved cracking speed on SHA-3 512 algorithm. The grammar here was trained on a MySpace dictionary, which leaked from an attack on MySpace portal containing real user passwords. The link speed here, which interconnected the nodes, was 100 megabit. And we tried the cracking on 1, 2, 4, 8, and 16 nodes. We have three different tasks here. One was to generate 1 million passwords, then 10 million and 100 millions of passwords. These two were, especially this first one, was very quick. So the more interesting results are on the top. We can see that in every case, we were faster. The blue is our solution with distributing preterminals, while the orange is the original solution. In every case, we were faster than the naive solution. And what's also visible here on this, because this is a serious task, while these ones are too short, we can see that the more nodes we have, the bigger the difference between the naive and our solution is. So it scales pretty well. Another graph here, it shows the same algorithm, the same grammar, but only 4 nodes. And here we analyze the effect of the link speed here. Yeah, so we can simulate the congestional network, for example, by lowering down the bandwidth. So this chart shows the cracking speed for 10, 100, and 1000 megabit line. And you can see with the 10 megabit, the results are excellent here. Yeah, so the lower bandwidth you have, the bigger the advantage of the preterminals is. So to conclude this, the idea behind our solution is that there is no need to distribute the passwords if the clients can generate them themselves. If you distribute a preterminal structure instead of the final passwords, it reduces the network traffic dramatically, and also the utilization of the server, because it moves the part of the load of the password generating to the clients. Yeah, so the idea here is that GPUs can crack while the CPUs can generate passwords. In all cases, our solution was either similar or faster than the naive solution. And the more nodes we have, the more noticeable acceleration we achieve. So we suggest this solution is very usable for use cases when you have many client nodes. And of course, for situations when you have faster hashes, faster means less complex algorithms, yeah, where the network often becomes a bottleneck. Okay, so that's all. Thank you for your attention. And if you have any questions, let me know.